If I have two openings here, and I have light coming through both of those openings, and a screen down here to detect that light, then what I'm going to get on that screen is a pattern that looks like this. Bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, and so on. On the other side, I'm going to get it's pretty symmetrical here. I'm going to get the exact same thing on the other side, bright spot, dark spot, dark spot, and so on and so on and so on. This that's straight across from the middle of the two openings, halfway between the two openings, is what we call, ladies, our central antinode, or our central maximum, or our central bright spot, or our central area of constructive interference. We assign a number of 0 to it. The bright spot that's right beside it, we call it maximum number 1, or bright spot number 1, or antinode number 1, or constructive interference number 1. Beside that, 2, 3, and on the other side, again, the exact same thing, maximum number 1, 2, and 3. In between each of those maxima are what we call minima, or dark spots, or destructive interference, or nodes, or nodal lines. They would have numbers that would be in between 0 and 1, 1 and 2. In other words, we'd make it 0.5, 1.5, 2.5, and so on. Now, when we're analyzing a question involving, this is what we call Young's double slit experiment, by the way. When we're analyzing Young's double slit experiment, we have two equations that will describe what's going on, the pattern that you see there. The first equation is d sine theta, lambda is equal to d sine theta over n. And the second equation is lambda is equal to xd over n times L. One of these equations is always valid. One of these equations is an approximation, but is a good approximation under certain conditions. Tell me which one is the valid one all the time. Christian? That's the one that's the approximation. That's only valid some of the time. In fact, it's always an approximation, but it's a really good approximation under certain circumstances. So we're going to say this is the one that's always valid. This is the one that's valid if ... What is that if? Yep. If theta is greater than 10 degrees, sorry, is less than 10 degrees, then I'm allowed to use that equation. It's still not perfect, but it's a very good approximation, a good enough approximation that you're going to get the right answer by using that equation if the angle is less than 10 degrees. Now, we had a little rule of thumb so that we didn't usually have to calculate what that angle is. Who remembers what that rule of thumb was? The nice little check for us, Rosie? Good. If you multiply the value of x by 10, and L is bigger than that number, then the angle will be less than 10 degrees, and you can use that equation. So what I'm suggesting you do, if you want to use this equation, is do this little check. If it meets the criterion for this little check right here, then don't even bother finding the angle. If it doesn't meet this criterion, if L is not greater than 10 times x, then get the angle, and then probably use this equation up here, d sine theta over m. We're going to run into a situation today in just a couple minutes where we have to get that angle, okay, where the second equation is not valid, where we have to get that angle. So I'll demonstrate where to get that angle from, how we would get that angle when we come across that question. All right, let's deal with some of these variables here. If L is bigger than 10 times x, what the heck is L? Where do I label L on this diagram here? Yep. Good. Distance between the screen and the opening. Good. What's D going to be? What's a little d going to be? Distance between what? Good. The distance between the openings. Excellent. What else to get? X. I guess we should label what X is if we're saying our criterion is if L is bigger than 10 times X. Christian, what's X? Yeah, it can be a length between antinodes right here, or it can be a length between antinode and node, or whatever you want, right? It can be whatever you want, as long as what? Yeah, Rosie? Yeah, As long as n matches up with it, as long as n corresponds to that. N is the difference in maximum or minimum number. So in this one, we'd say 3 minus 0 is 3. In this one, we'd say 2 minus negative 1.5 gives me a 3.5 value of n. It doesn't really matter what x you're using, what distance you're using there, as long as n corresponds to or matches up with that. And lambda, of course, is simply the wavelength of the light that you use. Now, this is assuming, this diagram here that we have right here now assumes that we use monochromatic light, right? If we use polychromatic light, what happens? How does it change things? Well, in terms of our analysis, it doesn't change things at all. In terms of the way this looks, it's going to look a little bit different, right? It doesn't change the way we deal with it, though. Okay, in the middle here, if we were analyzing this using polychromatic light, the central maximum would be white light. That is, if we're using all the colors of the rainbow, the central maximum would be white light. The first order maximum would consist of the colors of the rainbow. Okay, red, orange, yellow, green, blue, indigo, and violet, but in reverse order. There's the first order maximum. And then the second order maximum would be right here. And then the third order maximum would be right here. And so on. We get the exact same thing on the other side. This is a lot like what happens when you have a prism, right? When light goes through a prism, you get the light splitting up into its component colors because of refraction. Every color refracts differently. When you get light going through a diffraction grating, you get almost the same thing, except that you don't get one spectrum. When you have a prism, white light goes through and you get one spectrum on the other side, right? Red, orange, yellow, green, blue, indigo, and violet. One spectrum, lots of different spectra, right? Each maximum is a spectrum. The other thing that you notice here is that when light refracts and splits up, you get red, orange, yellow, green, blue, and indigo, and violet, Roy G. Biv. When it splits up as a result of a diffraction grating, then what happens? It's the opposite, right? Instead of Roy G. Biv, it's Viv G. Yor. Okay? Now, Christian, I'll get your question in 1 second. How do we analyze this? No differently. No differently. Pick a color. If you're given information about red light, then pretend all these other colors don't exist. It's only red that exists. If you're given information about blue light, then pretend only blue light exists. Ignore all the other colors. You may have all these different colors drawn on your paper. Scratch them out. Scratch them out and use only the color that you have data for. Now, Christian, you had a question there?
So is the light only on the nose?
The light is only on the antinodes. So these are our bright spots right here, which is what we call antinodes. And in between, those are what we call the nodes. Those are the dark spots. That's where we had destructive interference. And if we have destructive interference, there is no light there because a crest canceled out a trough. So what we have here is crest and crest come together, and/or trough and trough come together. What we get here is crest meets trough, and the light cancels out. Okay? Yep.
Like filter the color spectrum.
Yep.
Pass through the wavelength of, let's say, blue.
Yep.
How would I don't understand what difference between blue and the red light.
Okay. So the colors, the question says, you get a polychromatic light, and the question says, what's the wavelength of blue? What you'd have to have in that question is X, D, N, and L for blue, if you wanted the wavelength of blue. Okay, or D, theta, and N for blue. If you were looking for the wavelength of red, then you'd have to have different values of X, D, N, and L corresponding to red light. Make sense? You'll be given information, whether it's 5 variables here, right? You're going to be given 4 of the 5 variables for one color or another. Go with that color and pretend the other colors don't exist. Okay. I mentioned to you yesterday that on your unit test, which is, by the way, coming up next Tuesday, okay, a week from today, you are going to get a question with polychromatic light. with multiple colors of light. I don't want you to get bothered by it. I don't want you to treat it any differently than we have like any other questions we did yesterday with this. Okay? If it's polychromatic light, just it's a picture. You're going to see different colors. Just scratch them all out. Pretend you only have the one color for which you have information. Okay? All right. I'm going to tell you about one more thing here that that hasn't arisen in any of the questions that we've done so far, but every once in a while it does arise. Okay, this question right here, let's get rid of these polychromatic and let's go back to one color here. Okay, let's get rid of this just to unclutter it a little bit as well. This question assumes the light source is where? Okay, where's the light source? Bottom of the screen, top of the screen, left of the screen, right of the screen, Julia? Yeah, I would assume that the light source is at the bottom of the screen. And it's assuming that the light source is red light, right? If we have an interference pattern that's only red, then it's got to be red light at the bottom of the screen. Good? Go ahead. Yeah, yeah, yeah. Now, there is a possibility that you could see a question where the red light is up here, but yet the interference pattern is produced right here. In a situation like that, what you've got is your diffraction grating or your double slits down here. Okay, and the light's reflecting off of that diffraction grating. Instead of going through it like it was here, okay, it's reflecting off of it like this. Now, it produces the exact same pattern up here. It doesn't change a thing, except that when you see the diagram, it tends to mess us up a little bit because you're thinking, oh, the light source should be down here. Okay? You would still make this the value of L because this is your diffraction grating. Even if it's not allowing light through, rather it's reflecting light. You don't do this as often now because we download music and we download movies, right? But if you look at a CD held up to the light, okay, what do you see? Sometimes you see a rainbow, right? Okay, that's actually a diffraction grating. The CD is actually a diffraction grating. Light reflects off of it, these tiny little pits that allow your CD player to know what music is on there. Okay, that is like having these tiny little scratches or etches in this diffraction grating right here. Light reflects off, and what happens? Well, we see a rainbow in that case because when we're looking at a CD under light from our ceiling, the light is all the colors of the rainbow, right? If you shone a laser beam off of it, you wouldn't see all those different colors. Okay, that's a diffraction grating. It's reflecting light. It's exactly the same. This would still be D. This would still be L. Okay, this would still be X up here, and so on and so on and so on. It's just that our light source is up here reflecting instead of down here and transmitting through. All right. We had 3 questions for homework last night. I want to take a look at those 3 questions right now. Particularly number 3. Okay, I want to do number 3 for sure. The answer to number 3 was incorrect. Number 1, it was? Which one was the one that was wrong? 3 or 1? Number 1? Okay, it's number 1 that I want to go over then. Any others besides number 1? Yep. Okay, number 3. Number 2, okay. We'll do all 3 of them. Number 1 says, an unknown wavelength of light is incident on a diffraction grating with 2,500 lines per centimeter. Right away when we see lines per centimeter, we're thinking not D, but rather 1 over D. The distance between the central antinode and the third dark node is 20 centimeters. That's going to be X. And L is going to be 50 centimeters. We're going to determine what N is here. So let's make this our central antinode, first order antinode, second antinode, third antinode. We're talking about the third dark node. 1, 2, 3. We're going to say N is 2.5. Central antinode, third dark node, N is 2.5. We can get the value of D pretty easily, right? D is going to be 1 over 2,500, which is, let's do that real quickly. 4 times 10 to the minus 4, but remember that's in centimeters. So it becomes 4 times 10 to the minus 6 meters. Now we want to find the wavelength here. Now, Ethan, you asked me a question earlier on. Like, what if you do have multiple colors, and how do you know if they want to find the wavelength of red light versus blue light, whatever? Okay, here's the question. Let's say that instead of having one frequency, you've got white light shining on it. Okay, we're looking for the wavelength of one particular color. This data that we have here corresponds to that one particular color. We got white light. We got all the colors of the rainbow. We're analyzing one color because that's all we know anything about. All right, when I see this, I want to say lambda is equal to xd over n times L, right? But I got to do my little check here. Here's L. Is L greater than 10 times x? Well, L is what, 50? 10 times x is, 200? Can I use that equation? No, the answer in the book assumed that equation. That's wrong. Okay, the angle is too big. Okay, it's too big. You cannot use that equation. So what do we got to do? We got to get theta. Here's the distance from the screen, from the openings to the screen. That value is L, 50 centimeters. Here's X. It's 20 centimeters. I can find theta by using the inverse tan function. I'm going to say theta is equal to the inverse tan of opposite over adjacent, 20 over 50. And I think when you do that, it works out to be 21, 22 degrees. Who's got that? 21.8 degrees? Clearly more than the 10 degrees, right? So this is out of the question. I cannot use this. Every once in a while, you might do your check. The check might not work, so you go find the angle, and the angle is 9.3 degrees. Close to 10. Can you use it? Can you use the first equation? Yeah, you could in that case, right? But here, you're not even close. Not even close. So now we got to go back to that other equation. Lambda is equal to d sine theta over n. D is, what do we say it was? 4 times 10 to the minus 6 meters. Make sure you're in meters here. Times sine 21.8 degrees over n. N was 2.5. And Del, what did that work out to be? .9 times 10 to the minus 7 meters. How many people got 5.9 times 10 to the minus 7? Good. How many people got, what was the answer? They gave 6.4. How many people got that one? Okay. That's assuming, again, that first equation that we tried to use was valid, but clearly it's not when we have an angle of 22 degrees. Okay. Be alert for things like that. Be aware of it. I'll tell you that 90% of the time, that equation will work. So if you make that mistake, you're still likely to get the answer correct. But if you do the check, you're guaranteed to get that question correct. Okay, let's take a look at number 2. How many lines per centimeter are there on the diffraction grating if the third dark fringe is located 5 centimeters from the central antinode? We're going to say X is 0.050 meters. We're going to say L is 0.60 meters. We're going to say lambda is 500 times 10 to the minus 9 meters, 500 nanometers. What are we looking for? How many lines per centimeter? What is that? Not D, 1 over D. But you know what? We'll get D first, and then we'll worry about getting 1 over D. Yep. Lambda is equal to XD over N times L. Are we allowed to use this? Well, let's do our check. Is L greater than 10 times X? L is 0.6. 10X is, well, it's close. It works, right? L is barely greater, Christian, than 10 times X, but it is. greater than 10 times x. 0.05 for x. We got to solve for d here. D is equal to lambda times n times L over x. 500 times 10 to the minus 9. Oh, what's n? Third dark fringe. Central, first, second, third, fourth bright. N would be equal to 2.5, third dark fringe. Look at when we do that. Everybody should try this if you haven't already. (1.5 times 10 to the minus 5). How many people got that? Okay, what'd you get, Christian? Okay. I wonder if, did you make that 2 or something? Or 3? I bet you made that 3, actually. Do you understand why that's 2.5? Okay. Yep. Yep. All right, finally, number 3 says a diffraction grating has 1,000 lines per centimeter. That's 1 over d. We're going to make that d. D would be 1.0 times 10 to the negative 3 centimeters, right? 1 over 1,000. Or we could make it 1.0 times 10 to the minus 5 meters. So get d. Get it in meters, but get it in centimeters first. Our wavelength here is 750 times 10 to the minus 9 meters. We want to find the value of x. We're going to make n 1. The separation between bright antinodes. So it's the third antinode and the fourth, or it's the 15th and the 16th. Doesn't matter. N is going to be equal to 1. L is going to be 3.0 meters. So we want to use lambda is equal to xd over n times L. We got to do our little check, but we got a problem with that. We don't know what the value of x is. I'll tell you what you're going to do here. This question. You have no other option. You have to assume this equation is correct. After we use it, then we'll do our little check. Okay? X is lambda times n times L over d. N is 1, d is 1 times 10 to the minus 5. Over little d, L, this should have been 3 over 1 times 10 to the negative 5. See what we get there. 750 times 10 to the minus 9. Get 0.225. Is that good? Okay. Do you know what, guys? We have to go with that. We have no other option. We have no other option. We can't use the other equation because we don't have the angle, and without the value of x, we can't find the angle. But just if it makes you feel more comfortable, let's go back and do the check now. Even though it's not really going to serve any purpose because we didn't have any other option. Let's go back and do that check nevertheless. Is L greater than 10 times x? Well, L is, 3 meters? 10x is, 2.25 meters? Yeah, okay, L is bigger than 10 times x. So it turns out we're okay. But in the end, if we weren't, we wouldn't have anything else to do. Ethan, question?
So with this question, instead of like
Yep.
number 1 they threw on the end, like what color of light is this?
Yep.
Would you just kind of guess, be like, oh, it's more towards
Yeah.
end of the spectrum?
We've seen that in one or two of the questions that we've done, right? What color of light is it? I wouldn't worry too much about that. I would make sure that you can identify that it's visible light as opposed to ultraviolet or infrared or something like that. But specifically what color, I wouldn't worry very much about that. I don't think I've seen a single question in 22 years that's asked us what color of light that it is on a diploma exam that is. I wouldn't say for sure, but I don't think that I have. Okay, I can tell you that I've seen a number of times what kind of EMR is it? Visible light, ultraviolet, and so on. If by chance they asked you what color it was, and it was close to the left, like to the 4 times 10 to the 14, then it's closer to red. And if it's closer to the 7.5 times 10 to the 14, it's closer to violet. Okay? I don't think they'd give you 4.2 times 10 to the 14 and say, oh, is it red or orange? Okay? They might say, is it red or blue? Okay, and in that case, like, it's probably not that hard to figure out that it's red, right? Um, I don't think they'll do that still. But if they do, then pretty confident that it would be towards the left side or the right side. Um, yeah, it'd be clearly one or the other. You wouldn't have to, you're not expected to remember bands of frequencies within visible light. I don't remember them. So we certainly don't expect you guys to remember them. Okay. If it's an extreme, it's a little bit easier, right? But if it's close to something else, it's pretty tough to distinguish that.
And then
Yep.
you have like a mixture of two colors, like
Yep.
red and blue. What kind of wavelength would that be?
Uh,
Would it just be like in the middle?
well, if you had a mixture of red and blue, it would be a combination. And what you,
Something that isn't on the spectrum, like not Roy G. Biv, but like brown, or like some weird color that isn't like red, orange.
well, that's a good question.
Like
That's a
a
good
brown
question.
shade, and it's like in that.
Okay. So, so what if it's not red, orange, yellow, green, blue, indigo, and violet? What if it's some kind of combination of those colors? Well, the reality is, if it's a combination of those colors, um, like brown, I don't know. To be honest, I don't know what colors you need to put together to make brown, but all of them. Okay. So let's say all of them. Okay. Um, then then what you got to do is pick one color. Like you've got when you put it through, you understand that when you put multiple colors, and that's what different colors other than red, orange, yellow, green, blue, indigo, and violet are colors other than that are multiple colors put together. When you put multiple colors through this diffraction grating or double slit, um, then it splits it up just like a prism does. It splits it up into its component colors. So it doesn't matter whether you've got brown or some other combination. Um, what matters is that you've got more than one color. And then we've got a situation like we had a minute ago where you pick a color because there will be clear data, not for the brown, but there'll be clear data for each of the colors within the brown. You may only have data for one of those colors, but there would be clear data, separate data for all of them. So even if you got something like that, some color that you don't recognize. Okay? When I was a kid, I had the Crayola box of 8 crayons. I was always a little upset because a couple of my friends had the 64 crayon box. A little choked at that. Okay. In the end, so I had basically Roy G. Biv. Okay. They had all these different combinations of Roy G. Biv. You put those colors through a diffraction grating or a double slit experiment, it's going to split them up into the Roy G. Biv colors. It's going to split them up into the component colors, and you just pick a color. Okay. Question?
How come, blacklight? How come when you have blacklight, how come you can like see certain stuff a lot better?
Yeah, I don't know. There's a chemistry thing there, and I'm not sure what that is. Yeah. Yep.
At least yours are like a sharpener.
Yeah. Well, no, my box of 8 didn't, but the 64s did.
Oh, what?
But if I treated my friends nicely, then sometimes they let me sharpen my crayon with.
Or if you're like good enough, you can steal one of them and then you have 9.
Dishonest enough, you mean?
Oh,
I had nowhere to put it though, because the
me
box
neither.
only had 8.